Good morning. Today we're doing Paul Hewitt's Conceptual Physics, Chapter 21 on temperature, heat, and expansion. So what is heat? Kinetic energy is the energy that comes from motion. So you remember if your bullet is flying through the air, that is kinetic energy, energy that is coming from motion. If you're falling, you have lots of kinetic energy. The faster you go, the more motion there is, the more energy you've got. Well, in the same way, heat energy is just molecular kinetic energy. Sometimes we call this thermal energy. Sometimes we call it internal energy. This is the energy that is stored in the little molecules and atoms of your substance, vibrating, shaking, jostling over each other. This is that kinetic energy. So just the same way that a baseball flying through the air has kinetic energy, the gas molecules pinging around have kinetic energy. In the same way that the little molecules in a crystal structure of a solid have energy, vibrating. So the more jiggling and jostling of your atoms or your molecules, the more jiggling and jostling that's going on, the more molecular kinetic energy they have. That is the more internal energy, thermal energy, whatever you want to call it, molecular kinetic energy. That is that energy. That is what we're talking about in thermodynamics. Okay, so those jiggling, jostling molecules are full of energy, and the more they jiggle and jostle, the more motion they have, the more internal energy they've got, the more thermal energy they've got. So think about like the molecules in a cup of really, really hot tea and the molecules in a cup of lukewarm tea. Which has more molecular kinetic energy? Well, the hotter tea. If you could look at a microscopic or zoom in, look at a molecular level, the water molecules in your really, really hot tea are moving a lot faster than your lukewarm tea. They have a lot more molecular kinetic energy or heat energy. Now, if you took your finger and stuck it into your hot tea or your lukewarm tea, you could feel the difference. What are you feeling there? You're feeling heat. Heat is the transfer. You're feeling the transfer of that molecular kinetic energy, that internal energy, that thermal energy, the transfer of that thermal energy. That is what heat is. That is what you're feeling. So when you put your finger into the lukewarm tea, they're jostling a little bit, they're pinging your finger a little bit, helping the molecules of your finger wiggle a little bit, but not that much. When you put your finger into the boiling hot tea, those jostling, wiggling, moving molecules are vibrating the molecules in your finger. And you feel that. You feel that that's as burning on your finger, or as heat. So remember, heat is the flow of thermal energy from a higher, from a higher temperature object to a lower temperature object. This is heat. This is what we feel as heat. This is why when you put your finger into that boiling hot tea, that heat, that jostling, it's jostling the little molecules in your finger, you'll feel it. This is why if you put your finger into ice water, what's going on? You feel cold. Well, cold doesn't really exist in the way that heat exists. In the same way that darkness is the absence of light, cold is the absence of heat, or less hot than its surrounding things. So what you've got here, when you put your finger into ice water, that cold that you're feeling is the heat being sucked out of your finger by that ice water that's now jiggling a little more, warming up a little more from your finger. So if you fall into the Arctic Ocean and freeze to death, you have warmed up that ocean by a little tiny bit, because it's huge. You warmed it up by a little tiny bit. As you both reach a thermal equilibrium, as it sucks the heat out of you, and as that you get all the heat sucked out of you and freeze, but you have made the ocean a tiny bit warmer when you fall in. Tiny, emphasis on tiny. Because things try to reach a thermal equilibrium. When we talk about equilibrium, we see this in like water. Like you'll see it if you have, if you break a dam and the water will try to be even with the lake. It'll rush down and it'll try to reach an equilibrium. The same way, heat is the transfer of that thermal energy trying to reach a thermal equilibrium. For your finger plus a boiling cup of water, plus your finger plus the ice water. Heat is that transfer of thermal energy trying to reach an equilibrium in thermal contact. You need to have thermal contact for the heat to flow. Another example of this is a lot of times my hands will get really cold in the evenings, and I'll reach over and hold my husband's hand, and he has a nice warm, I think his body runs at a higher temperature than mine. And he has very warm hands, and over a few minutes I can feel that warmth warming up my hand. Well, from a molecular level, what's going on? The molecules in his hand are vibrating much quicker than the molecules in my hand, but as I'm holding onto his hand in thermal contact, the molecules in my hand are now vibrating more, and he's warming up my hand. I'm cooling down his hand a little bit. The molecules in his hand are now not, they've used some of that energy, that kinetic energy, by warming up my hand. I think one of the most beautiful examples of self-sacrificial love, I wish I remember their names, they were these explorers, 2 guys, and they were exploring somewhere, I think in the Antarctic, so extremely, extremely cold. And one of the guys, boots, I don't know if it got wet, water got in his boot or something happened, and one of the guy's feet, or one foot in particular, was so close to freezing. And once it really, really freezes, you can lose the whole limb. And they were out somewhere super, super cold. You're just bundled up against the cold. And they're we need to warm up his foot or he could lose the foot. And his friend, the other guy, actually unbuttoned his shirt, his own shirt, and if you've ever been really, really cold, you know how you do not want, you're just trying to keep your organs warm. And he opened up his shirt and stuffed his friend's almost frozen foot down his shirt to try to give some of that thermal energy from his own body into warming up his friend's foot, and he saved his friend's foot. But I mean, that's love. You care about your friend's foot more than if you've ever really, really been super cold, what it feels like. But here, this was thermal transfer. He was giving better thermal contact, so all that heat from his body would go into his friend's foot and warm it up. Because the heat is going to flow toward thermal equilibrium. So if you think about it, originally the guy's foot is getting cold in thermal equilibrium with all the ice and snow and cold, cold wind in the Antarctic. And all that heat is being sucked out of his foot, so now he's got him into his friend's shirt, and now he's sucking the heat into his foot. Okay, so this is how thermometers work, by the way. How do thermometers work? So we've talked about what thermal energy is. Remember that heat always flows from a higher temperature to a lower temperature. So you take that, red hot sword that's in the furnace, and it's in this huge hot furnace. It's heating up, and they pull it out, and it's glowing hot red, and then they plunge it into a bucket of oil or water, lukewarm water or oil, and you hear, and it's cooling down. What happened? Well, you took that cold iron, you put it into a furnace that's super, super hot, and it tried to reach a thermal equilibrium, so that you've got all that thermal energy from the furnace flowing into that blade. He pulls the blade out, now he wants to cool it down. He quenches it into this lukewarm oil or water, and now that thermal energy is being sucked or used up and vibrating all that oil or that water. Sometimes you see steam rising off as he sticks it in, because that thermal energy is being transferred out through heat transfer into that. And so that is all thermal contact and the heat traveling from a higher temperature object to a lower temperature. So when you had the cold sword in the furnace, higher temperature furnace flowing into the lower temperature blade. Now you take it out, you've got a hot blade, plunge it into the cool oil. Now you've got the higher temperature blade, the heat flowing out into the cooler oil. Okay, so thermal heat transfer depends on how good something is at that thermal contact, at that heat transfer. Not every substance has the same rate of heat transfer. We can be very grateful for this. This is why we can survive going into a desert, in Phoenix, sometimes 118 degrees. You will be drinking water like crazy, but you can, sweating, but you can survive out there. If you are an equivalent temperature of water, for that same period of time, you'd probably be dead. Because air, even though the air and the water are both at the same temperature, the air is much, much better at insulating, or to put it another way, is much, much worse at heat transfer, at transferring the heat that's in it to the heat that's in you. Where water is much better at that, solids and water tend to be much better at that. So for an example, if you open the oven and you want to make sure it's on, So you might stick your hand in and go, yeah, it's hot, and take your hand out. You're never going to open the oven and stick your hand on the metal oven rack or the metal pan and say, is that hot? I mean, if you do that, you're going to get a burned hand. But you will do that for the air. Why? Because the air inside of that oven, 350 degrees, is the same as that metal pizza pan or whatever you've got here at 350 degrees. So why is it that the air, you just feel hot, you pull it out, and the pan, you will not touch that? Because the solid of that metal pan is much, much better at heat transfer, at quickly transferring all that thermal energy into your hand than the air is. We often use the word poor conductor. A poor conductor is a good insulator, and a good insulator is a poor conductor. Conductor means it's good at that transfer. So air, we say, is a poor conductor, but air is a good insulator. Metal is a poor insulator, but metal is a very good conductor. And the reason metal is actually a good conductor has to do with the fact that metal atoms, their electrons on the outside are actually held more loosely. So they've got more like these crazy electrons running around in metal that helps with the vibrating and whatnot much faster than air. So that's kind of cool. There's actually it's down to the atom is why metal is a better conductor. Anyways, so back to heat flowing and equilibrium. Solids and liquids are better at heat transfer than gases. This is a lot of insulated things that we think of as good insulation. So like fiberglass insulation or feathers or cellulose insulation. If you take fiberglass insulation, if you just take melted solid hot fiberglass, it's actually not a very good insulator. But when they make fiberglass insulation, what they're actually doing is extruding it with mixing it with air. So you've got this fluffy stuff. So when we think about it, we know that fluffy stuff makes good insulators. Why? Because you've got all those trapped air pockets. It's because gases and air is a much worse at conducting, at heat transfer. It's much better at insulating. So all those pockets of air, almost like this microscopic bubble wrap, is what keeps you warm. That's why fur keeps people warm so well. It's a good, sorry, but I say keep you warm, I mean it's a very good insulator. It stops heat transfer. So when you go out in Siberia and you're wearing a warm fur coat, that fur coat is acting like an insulator. It's making it much slower for the heat to transfer out of your body into sub-zero temperatures. And that's because fur has a lot of air pockets in it, actually. That's why they've gotten better and better with synthetic fabrics, is they're cropping feathers and fur. They're figuring out how to trap more air in it. Okay. One of the many things they're doing with that. Okay. So let's talk a little bit about, thermometers. So in the same way we're talking about not everything conducts heat as well as everything else, we're also going to talk about the fact that when things get hot, they expand. We know that. When things get hot, they expand, because their molecules are getting bouncer and bouncer and moving away from each other. So we know that, they expand, they get less dense. We know this from taking a pot of water and boiling it, and then it becomes a water vapor or gas. We know as something gets hot, it expands. This is true for solids too. As you heat something up, it will expand. This is why bridges need expansion joints. Because you get really, really hot, it's sitting there out in the sun, the steel bridge, it's starting to expand, and you don't want to build your bridge happily in the winter. It's great all winter. Summer hits, you get a heat wave, and your bridge starts to expand and buckles and cracks. You don't want that. And so a lot of bridges, they actually anchor them down on steel bridges. They'll anchor it down on one side, and the other side they'll sort of have this weird almost a floating, it's hold up, but it's not anchored. What's the word they use for that when they do it on bridges? I can't think of the word, but it's kind of like an expansion joint. So you're building in some flexibility. You're building in some flexibility that bridge can expand in the heat of summer. Another thing that we see expanding as it gets hotter is if you are. Okay, pause it. Because substances expand when they get hot. This is another reason that if you're stringing telephone lines, if you live somewhere where they've got those, you've got your telephone and you're stringing your telephone lines above the ground. So this is your telephone poles. This is your telephone line. And if you're stringing it in the summer, you'll actually want to give it a little bit of slack, like this, because that it's hot right now. The sun is shining on those wires. They're more expanded, and that when it gets cold, they'll pull tight. So you don't want to string it tight in the summer. What will happen in the winter if you do that? Snap, 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 snap. You don't want that. So that's why they put, in fact, I think you might even be able to go out if you live somewhere, although measuring it accurately would be difficult. You could even measure like how much they sag depending on the outside temperature. Because when things get hot, they expand. A way that we use this with thermometers, analog thermometers. So I'm not talking digital thermometers. If you still have the thermometer where there's like a little red, you know, the little old-fashioned thermometer. A lot of times outside thermometers are still this way. You'll see a little column of what looks like a little glass tube, and you have your little markers about what, you know, how many degrees it is. And and I guess if this is a human thermometer, we go up more. Okay, so 90, 100. Okay, so what happens is that as you stick it in your mouth, or if this is outside, you stick it in your mouth, what happens is that now thermal equilibrium, right? So now the molecules in your mouth are jostling and heating up that thermometer to the same temperature as your mouth. And what happens is they usually have like a tube of either colored alcohol or liquid mercury. Liquid mercury works better, but they had too many people biting thermometers and liquid mercury going everywhere, which is poisonous. But anyways, so as you put that in your mouth, or so say you pick it up and it's at ambient temperature, 70 degrees outside. Okay, so you stick it in your mouth, and as you heat it up, you're heating up that mercury. Well, what happens to that mercury as it gets hot? It expands. And so as it expands, it shoots up, and it shoots up exactly to the line, and it'll show you what temperature your body is. Because we'll mark, yes, what's your question?
What happens if it gets even hotter than the highest temperature?
Well, usually they go higher than your body. I mean, if your temperature is like, you can pull one out and look, it probably goes up like 120. I mean, it depends on the thermometer. Like a candy thermometer goes from like 100 degrees to 400 degrees.
But if it did get hotter, what would happen?
Theoretically, if you raise the temperature of that thermometer higher, of that analog thermometer higher than what it was meant for, it would burst. If you've ever watched the old Peter Pan movie, it's supposed to be funny. They've got a part where Smee is trying to help Captain Hook, and he puts a thermometer in his mouth, and then he starts pouring really, really hot water at his feet, and then Captain Hook turns like bright red, and then the thermometer explodes because it got too hot. Now, in real life, obviously, it's not. It's not gonna. Captain Hook is not just a chunk of iron getting hotter and hotter. It was a cartoon, but it was kind of funny. But it's this principle. But as we can see, when you put it in your mouth and the glass of that thermometer and the mercury of that thermometer reached your thermal equilibrium with your body, the glass did not expand exactly with the same amount of heat the way that the liquid mercury did. If it did, then the whole thing would expand and it would just still sit at the same level. But because the glass is also expanding, but it only expands a little bit. Well, the liquid mercury is expanding a lot. Different things expand at different rates. We'll get to that. Brass, for example, will expand and contract much more with temperature than iron will. And we'll get to that later, why this is so important in electronics. Okay, so heat transfer. So let's talk about calories. What is a calorie? A calorie is a unit of energy. So 1 calorie is the amount of energy that it takes, energy that it takes to raise 1 gram of water. Think 1 gram of water, 1 degree Celsius by 1 degree Celsius. Okay, so to take that one little bit of water and raise it 1 degree Celsius, that amount of energy we call a calorie. If you remember from last semester, we talked about joules. You also can measure energy in joules. 1 calorie is equivalent to, I think it's 4 joules? Yeah, about 4.18 joules. So joules and calories are measuring the same thing, energy. Another term that you've probably heard if you work at all with like heaters is BTU, British Thermal Units. British Thermal Units are about equivalent to, I think it's a lot more joules than that. How much are British? It was, 1,000 joules. 1,000 joules. And you might say, whoa, because a British thermal unit is the amount of energy required to raise a pound of water by 1 degree Fahrenheit. So you can see here with our calories, we're only talking 1 gram of water. Yes?
You mean Celsius?
BTUs are done in Fahrenheit because they're British. They're British. So they say 1 pound of water by 1 degree Fahrenheit. So you'll see that raising
Celsius
the entire
is
pound.
bigger, right?
That's why BTUs is 1,000 joules.
Wait, but a Celsius is bigger than a Fahrenheit, right?
A little bit.
Because isn't like 100
Yeah, a little bit. Right, 100 Fahrenheit is about a 200. No, about 100. 180-ish Fahrenheit equals 100 Celsius. So I guess almost twice. Okay, so this heat energy, now when we talk about calories in our food, we're not talking little c calorie, we're talking big C calorie. Big C calorie, and you'll sometimes see this if you look at food packaging in like European or Korean or other stuff, is they will sometimes write kcal, and you're like, what in the world is a kcal? Kilocalorie? Kilocalorie means 1,000 calories. For whatever reason, in American food packaging in the Western world, instead of writing kcal, we write it a big C calorie. So a little C calorie is to make 1 gram of water raised by 1 degree Celsius. On most of our food packaging, our big C calorie is 1,000 grams of water by 1 degree Celsius. So you can imagine that if a calorie, or let's say the big C calorie, okay, kilocalorie is the unit of energy needed to raise 1,000 grams of water by 1 degree Celsius. You could see that your body, roughly being made of water, needs a certain amount of energy, and you calculate the ambient temperature, and now calculate you want to be at least 97 degrees, or 96, whatever, you want to be your internal body temperature for it to function, you want to be at least 96 degrees. You could sit there and you can work out how much calories you need, roughly. I mean, you're not 100% water, but do that. How much calories do you need to stay alive? And there's also the heat transfer. How much are you losing in heat loss? If you wrap yourself in blankets, then you're not losing as much. You could see why people that live in extremely cold places have to eat a lot more calories to stay alive, to keep their body in that optimal range. Yes?
It's been 21 or 22 minutes and you've only got 26 minutes.
Okay, thanks. I'm almost done. Okay. Your little heat lamp. So there's a fun calculation in chapter 21 where he says, okay, if this lady eats these many calories a day, how much heat is she radiating? Because you're a little heat lamp, and he figures out that he says equivalent to a 100-watt bulb. This is an incandescent bulb. So an incandescent bulb, if you remember those before the days of LEDs, can make things quite warm. Another example how you're a little heat lamp is when all of my daughters at night and in wintertime go into a room, it's wintertime, so they're all wearing their long sleeve jammies and everything, and it's a little room. And as they stay in that room, within a couple hours, they are shedding their long sleeves and they just want to sleep in their short sleeve under jammies. And why is that? Because their little bodies have heated up that room significantly, because a human body is a little heat lamp. Okay. Now, all right, so now we're going to talk about specific heat. What is specific heat? Specific heat capacity. So specific heat capacity is basically how much heat energy or thermal energy do you have to pump into that object, that thing, in order to raise its temperature. Because it's not the same for everything. For example, so we like to define, for example, water needs, remember how what we defined a calorie by? Water needs 1 calorie of energy to raise its temperature 1 degree Celsius. 1 gram of it by 1 degree Celsius. Iron, on the other hand, needs only 1/8 of a calorie to raise 1 gram of iron by 1 degree Celsius. So you see that water has a much higher specific heat than iron, and you will feel this if you go outside and you got a cup of water and a chunk of iron and you leave them in the sunlight, and you come back, I don't know, an hour later or 10 minutes, I don't know, depending how strong the sun is, you could feel the heat of that iron, and you could stick your finger in the water and it's not that hot yet. The water's still soaking up that sunlight energy. It's still soaking it up. It's soaking it up. It's soaking it up. Just to raise the temperature of that iron, you only need 1/8 the energy that you need to raise the temperature of that water. So sometimes we'll often say that objects that basically need a lot more heat energy pumped into them to raise their temperature, we'll say they have a very high specific heat capacity. It's as if they're a giant sponge sucking in that thermal energy to raise their temperature. And in the same way, they have to lose a lot of energy to drop their temperature, because they're like a giant capacity, like a big, huge bowl. You can kind of think of it, if the iron, you can kind of think of it as that when we're trying to raise the temperature of something, like we've got a big bowl here and a narrow little cup. We're saying to raise that temperature, you got to pour more liquid in, to raise that temperature by a degree. You can kind of think of it that way. That's why we use the word capacity, heat capacity. How much heat, thermal energy are you having to pump in to raise the temperature of that object? Now you might ask, why? If you zoom in on a molecular level, the answer why is that iron is in this very orderly crystal structure. And its temperature, when it reaches a certain number of vibrations, that's what it takes. When you look at water, all that energy you're pumping in, it's doing bond stretching. It's like they're doing little somersaults over each other, doing crazy stuff before they get to that vibrations. So you're having to pump a lot more heat to get that same temperature. And remember, though, it's like when the same way that you're having to pour a lot more water into that higher heat capacity, and this is just a visual aid about the same way you're having to pump a lot more heat, it also means that to cool it down, you need to bleed. So the higher the heat capacity, like a bigger bowl, you have to pump in more thermal energy, more heat energy in order to raise that by 1 degree or by any degrees. This is why we like to use water, because water is so good at soaking up so much heat energy before it rises a degree. This is why we like to use water in coolant systems, like cooling an automobile. When you have your radiator fluid is mostly water. Why? Because it will soak up a lot of heat from your primarily iron engine before it will rise by that degree. And when you try to run it through the radiator coils to try to bleed some of that heat off, this is why you're in trouble if the coolant system, if all your radiator fluid boils out. Pull over to the side of the road and pour some water, even from your water bottle, it's better than nothing, into your radiator system, because that is what helps cool your metal engine down and keeps it from overheating and breaking your car. So the water can soak up a lot of that heat. That's why we love water for coolant. In the old days, moms used to send their kids to their beds in the cold winter nights, with a hot water bottle, because that hot water they poured in that hot water bottle is holding a lot of thermal energy. And so it's slowly losing that. Remember, it takes a lot of heat to heat up, to pump into that water, to heat it up. And the same way, a lot of heat will bleed out of that water before it cools down. And all that heat that's bleeding out of the water all night is keeping their little kid warm with that water bottle. So different materials, as we've seen with the iron and the water, have different heat capacities, specific heat capacities. You know this if you ever baked anything in like a big cast iron pan or like a little thin pan. You know when you turn the heat off, not wanting to overcook the eggs, because you know that if you've got that thick cast iron pan, it's going to take, even when you remove it from the heat, it's still going to be cooking. It's still going to take some time bleeding that heat off that you pumped into it by turning your oven on. So another example is that, like, if you've ever taken like a piece of pie or calzone out of the oven and you tentatively touch with your tongue the crust and it's a nice temperature and you stick it in your mouth and bite and the liquidy inside squirts all over your mouth and burns your mouth, that's because the crust that had less water in it was able to cool down much faster than the very high in liquid insides. That, like the melted cheese or with a pie, the liquidy pie filling has that high specific heat of water. There's still a lot of thermal energy in there. Okay, this is also water holding on to so much heat. This is why the Gulf Stream, that's a very hot stream of water that comes from the Caribbean and it goes up past Europe and keeps Europe nice and warm. Much warmer than it would otherwise be. Otherwise, it would be like northern Canada, which is like a frozen wasteland. But if you look at where it is on the globe, yet somehow, instead of being a frozen wasteland like northern Canada, you've got beautiful Britain. Why? It's because the Gulf Stream, that warm water, is still slowly bleeding off its heat that it picked up in the Caribbean. And by the time it goes past Europe, it's still radiating all that nice heat out. The inverse of this is why California is such a nicer place to go in the summer than Arizona, is that even though California and Arizona are getting the same amount of sunshine, in California you've got that Pacific Ocean next to you, so all that heat energy being pumped into the land, or you've got the ocean next to you, the water is sucking a lot of that heat energy, where in Arizona we're just getting heated up more and more and more. We've just got mostly air and dirt, where all that water is nicely soaking up a lot of that extra heat for Californians, which is also why Californians have milder winters. They have cooler summers and warmer winters than we here have in Arizona, because in the wintertime, when we are cold or whatever, that warm ocean is still radiating heat. So it acts kind of like it takes their highest temperatures down lower, and it brings their coldest temperatures up higher. And that is why it's so easy to grow things in California. It's in a very nice mild climate, and it's because it's next to the ocean. Okay, so we've talked, I wanted to just quickly say something about the bimetallic strips and circuits. So we talked about how different things expand at different rates, and brass will expand and contract much more with heat than iron will, or steel. And so what they'll do is they'll make these little strips of metal, where like this side will be, here, do it with this. This side will be brass, and this side will be steel. And what will happen is that as it gets hot, as you heat it up, it'll curl this direction because the brass is expanding more. Wait, no. Sorry, that's when you cool it down. When you heat it up, as you see, as the green here, the brass expands, it'll do this. And then as it cools down, it'll shrink and it'll do this. And they use these inside of circuits to close and open circuits. You know, when you've got so you've got a thing here and a thing here, and you want it to make contact, and then depending on the temperature, then it'll flip up. And I think they have these in thermostats. Like when your house knows when to fire. I don't know how it is now with all the smart meters and stuff, but this is how the old-fashioned thermostats had when it knows to start up the heat to turn it off, is that as the temperature is cooling or heating, you can be shutting and opening a circuit. That was pretty cool. And last thing, he talked a little bit about the very interesting crystal structure of water, that when most things as solids are more dense than they are as liquids, because as you heat it up more, it expands, it becomes less and less dense. Water is an exception, which we can be grateful for. Otherwise, lakes would freeze solid because the top, for the cold air, the top layer of the lake gets frozen, and then it just floats. And so the fish can still survive underneath. If water did not have that weird crystalline structure when it freezes, that's why your ice floats. If your ice sank, then the ice would just keep falling and crushing all the fish to death until your lake was just one giant ice cube with dead fish on the bottom. So that's really cool, that the crystal structure of water being so weird and floaty and hollow compared to other things when they're in solids, saves us, allows there to be any sort of, animal life in water in places that freeze. All right, cut. Okay.